Let's go ahead and we're going to cover 8.3. We're going to get through most of it today. We should be able to finish off all the ideas that you need to start the homework. We'll do a couple more tomorrow. And I think hopefully you find this kind of interesting. This is a very advanced topic. This is not something that you're going to see in the textbook. The textbook shows you how to find the inverse of a matrix in a particular way that works just fine, but is also unbelievably tedious. Okay? And the likelihood of you getting the right answer using the book technique, I think, is much less than if you use this technique right here. So if any of you end up going on into math or science or something like that, you have to take some differential equations classes, linear algebra or something like that, you're going to see the same type of skill pop up. So we're going to be talking about how to find the inverse of a matrix. Okay? And the first thing we're going to do is we're going to do this problem right here. We're going to multiply these two matrices together. What do I need to do first before I even try to see or try and multiply them together?
Make sure that they can be multiplied.
Make sure that they can be multiplied. So I'm going to check the dimensions. And remember, it's rows and columns. So this is a 2 by 3. This is a 3 by 3. The inner dimensions are the same, so it can be multiplied. The outer dimensions are the dimensions of the resultant. So I end up with a 2 by 3. So let's make that look right. 2 rows, 3 columns. So I'm going to end up with something like this, and then I just fill those in. So if I want to find the entry right here, this is first row, first column. So I'm going to take the first row and multiply it with the first column, right?
Yep.
So something kind of cool happens the way this matrix is set up. I have 3 times 1, that's 3. Negative 1 times 0, 1 times 0. So altogether, what do I get?
3.
I end up with a 3, okay? Next thing I want to do is I want to go through and find this one right here. So I'm going to take the first row and multiply it with the second column. So let's see what happens there. So I have 3 times 0, negative 1 times 1, and then 1 times 0. So the only one of those 3 multiplication problems that produces a number that I need is the middle one, so I get a negative 1. Okay? Everybody good there?
You should put one of these on our test.
Okay. All right, so let's take a look at this one. First row, third column.
1.
First row, third column, we get a 0, and a 1. Second row, first column. Second row, first column, we get a 0 times a 1, and then the other 2 are 0, so this is going to be a 0. You notice what's happening?
I think it's going to be the exact same.
Okay, let's just double check. So this is going to be second row, second column, second row, second column. Now notice how this works, how this matches up. Second row, second column. Second row, I'm going to have this one, and the only one that it's going to work out to be multiplying by a number other than 0 is this one right here. So I end up with a negative 2, and this last one, if you check it, we end up with a 5. Okay? So what I did is I took this matrix right here, I multiplied it by another matrix, and I got right back to exactly the same matrix. Okay? When we multiply something and we get exactly the same thing we started with, what must we have multiplied by? A 1, right? Now, this isn't just a 1, but it is the matrix equivalent of a 1. Okay? So it's called a multiplicative identity. So if I did 5 times 1, I end up with 5. The number 1 is called the multiplicative identity because whenever I multiply by 1, I end up with the same answer that I started with. The number that I multiplied maintains its identity, if you want to think of it that way. Okay? So that problem right here has an interesting answer. That second matrix acts like a 1. Acts like the matrix equivalent of a 1. And what it's called is, it's called an identity matrix. Okay? So here are a couple of examples of identity matrices. Okay? So if I write I2, that's a square matrix that's a 2 by 2. The I stands for identity. The 2 means it's a 2 by 2. Identity matrices are always 2 by 2s. Always square matrices. So 2 by 2, 3 by 3, and so forth. So in I3, that's the 3 by 3 identity. So again, that's 1's down the diagonal, 0 everywhere else. And it's that diagonal that makes it so when we were in the second row, second column, there's that one that's in the second row. Okay, second column, and it happens to get multiplied by 1 in this place right here. So it turns out that every one of those numbers works out exactly the same. So what do you think I4 would be? A 4 by 4 with?
1's.
1's down the diagonals, 0 everywhere else. And what do you think I1 would be?
1.
It would just be a 1, right? It would just look like this, okay? So if you ever see something like this, and we're talking about matrices, you know I means identity. The subscript indicates how the dimensions of that square matrix. Everybody good there?
What kind of real world application uses 6 by 6 matrix? Like have 6 equations that you have to solve for equations?
Lots of them. In fact, there are tons with way bigger dimensions than that. Okay.
Exciting.
Yeah. Okay. Luckily, we learned how to use a computer to make it do that. Okay.
Thank
So,
you, computers.
next question here. Remember, is matrix multiplication commutative? Can you move the problems or the matrices around in a matrix multiplication problem and still get the same answer?
No.
The answer to that is a big fat no. And we can tell that right above here, because if I put these in the opposite order, I would have a 3 by 3 being multiplied by a 2 by 3. And are the inner dimensions the same?
Nope.
They're not, so you wouldn't be able to multiply them. Okay, so matrix multiplication is not commutative. Okay, now you'll notice that in all the discussions that we've had in chapter 8, when we're talking about matrices, we really haven't talked about anything in terms of matrix division. Okay, we don't do matrix division very often, but if we do have to do matrix division, it turns out you can't divide by a matrix. So we have to be a little bit clever in the way we do this. Okay, now if you've ever had somebody who's a mathematician or a math teacher say, hey, there's really no such thing as subtraction and there's really no such thing as division, that's actually true. Okay, if you're going to subtract 3, what we really do is we add the opposite of 3. So on a problem like this, think about this. If we were going to solve this equation, most everybody here would go through and we just divide by 5, right? Well, what if I said you can't do this using division? You have to solve this one using multiplication. What could we multiply by that would effectively do the same thing? Autumn Rose? We'd multiply by 1/5. Okay? So 1/5 is the multiplicative inverse of 5. So timesing by 5 makes a number 5 times bigger. Timesing by 1/5 makes it 1/5 as big. So these two are inverses of each other. And if we multiply both sides by 1/5, these two will cancel off. And by the way, what will they cancel off to be? They will cancel off to be a 1. And then I can do the multiplication here, and I end up with a 6. Yes?
Is this why we didn't divide earlier when we were doing matrices?
That's right. Okay. It takes matrix division. Okay, is a very complicated process that we have to turn into multiplication, and that's what we're talking about now. Okay, everybody good? Okay, so what we're going to do is we're going to look at this problem right here. And we're going to pretend like these are all matrices. And we're going to talk about how to set up a matrix equation in just a second. So if I had A times X equals C. Now remember, letters toward the beginning of the alphabet usually represent numbers. Letters toward the end of the alphabet usually represent variables. So this is a number times a variable equals a number. Or this is a matrix full of numbers times a matrix full of variables equals a number matrix over on this side. Okay, now I'm going to write this problem up here again, and I'm going to do this problem a little bit different way with just slightly different notation. Okay, so you can think of this in terms of inverses. Okay, what if I were to take this and multiply it by 5 to the negative 1? Isn't 5 to the negative 1, isn't that 1 over 5? Okay, and don't we use the exponent negative 1 to indicate, even with functions, it's not an exponent, but we put that negative 1 up there to indicate that we mean inverse. So the inverse of 5, the inverse of multiplying by 5 is 1/5, and I do the same thing on the other side. Okay? So if I were going to do this one that way, if I wanted to turn that A into the equivalent of a 1, like we did up here, here's what I'd do. I'd multiply by A inverse on both sides. Now, what would these two do to each other? They'd cancel each other out to be the equivalent of a 1. Just like they did up here with the numbers that we're familiar with, they would cancel each other to be a 1, or the matrix equivalent of a 1. And then I'd have a variable on this side, and you'll notice that over here I would just have numbers. Okay? All right. So now let's get to the point where we can actually talk about how we can solve a system of equations using inverse matrices. Okay, so We don't need to divide by matrices very often, but if we do, it turns out what we're going to do is we're going to multiply by the inverse of that matrix. Okay? This can be, although not always, it can be a pretty cool way to solve a system of equations. Okay? Especially if you got use of a computer or a calculator or something that can find the inverse very quickly, or, like will happen on any of the more difficult ones, I will give you the inverse. Now, you do need to be able to find the inverse, but if you were going to solve one of the more difficult systems, I would actually give you an inverse. Okay? I want to make sure that you know how to find an inverse, but then I'm not going to kind of rub your nose in it by making you do them over and over and over again, because this is a fairly complicated and difficult process. Okay? So the first thing we're going to do is we're going to learn how to write what we call a matrix equation. And a matrix equation consists of a couple of things. It consists of a coefficient matrix, and some of this stuff is going to look kind of familiar in the terminology, a variable matrix, and an answer matrix. Okay, now that sounds like we're making things really complicated. We're taking a system of equations that looks something like this, and we're going to turn it into 3 different matrices so that we can represent it using a matrix equation. But let's go ahead and do this. So we want to come up with a coefficient matrix. Now, we've already talked about what a coefficient matrix is, so I'm going to do this. That coefficient matrix is just the coefficients that are on the variables. So this is going to be a 1 for the x, a 1 for the y, a 1 for the x, and a negative 1 for the y. Everybody good there? Yep. Okay, now, I need to have a variable matrix. Okay, the variable matrix is going to consist of variables. How many variables do I have? 2. I have 2. Now, watch please, I could do this. I could write x, y, and make it a matrix that way. Okay, now, this is a 2 by 2, right? This is a 1 by 2. Does that make sense to do it that way? It doesn't. So what we're going to do is we're going to do a column matrix, and we're going to do x here and y here. And then that's going to be equal to, okay, the other one that we need to have is an answer matrix. Now let's figure out how we need to write this. If this is a 2 by 1, the resultant, or the result is going to be, since the inner dimensions are the same, the result is going to have the same dimensions as the outer one, so this is going to be a 2 by 1, right? So that means it's going to be a column matrix. 2 rows, 1 column, and what do I put right here? 8, 4. Now, I think everybody would agree that the coefficient matrix is pretty easy. The answer matrix is pretty easy. And this really has to be this way so that matrix multiplication works out on this problem. Does everybody understand how to take a system of equations and write it as a matrix equation? Everybody good? Okay, now, here's what it says. Verify that your matrix equation represents the system. Okay, and this goes back to something that was a fairly simple topic that we talked about last week. It was about how we tell whether 2 matrices are equal. Okay, they had to have the same dimensions, and they had to have the same numbers in them, element by element. We checked equality element by element. So here's what we're going to do. Let's go ahead and multiply these together. If I multiply these together, I'm going to end up with a 2 by 1. Okay, and let's write down what we get. Okay, this is going to be first row, first column. So I'm going to take the first row and multiply it by the first column. So I'm going to take 1 times x and 1 times y. And what do I do with those? Add them together. So this is going to be x plus y. Am I right? Okay, next one. This is second row, first column. So I'm going to take the second row, multiply it with the first column. So that's going to be 1 times x, negative 1 times y. Add them together, I get x minus y, right? And then on the other side, it was also equal to this 2 by 1. Are the dimensions the same on either side? They are, okay? And this says 8, 4. Now, the only way to check and make sure that these truly are equal to each other is to say, well, this one right here in first row, first column has to equal this one right here. And this one in the second row, first column has to equal this one right here that's in the second row, first column. So this would be x minus y equals 4. Now, what I have effectively done is, what have I done, Jared? Gone in a big circle, okay? So all we were doing right here is proving that if you have this system right here, you can represent it as this system right here. This work over here was just double checking that it actually does represent exactly the same system. Okay, does everybody buy that? Okay, so we've laid some groundwork here. Now we're to the interesting part. Everybody ready?
Yep.
Okay, because we're going to use some terminology that most people don't hear in high school. Okay, so here's how we find the inverse of a matrix. Okay? So we're going to find the inverse of the matrix of coefficients. Remember, it's this matrix right here, that matrix of coefficients, that we've got to find the inverse of. So here's how we do it. Okay? If A is a matrix, then A inverse, okay, the inverse of that matrix is 1 over the determinant, and I'm going to put a comma right here, times the transpose, so there's a word that you probably haven't heard before, times the transpose of the matrix of cofactors. 1 over the determinant, we know what a determinant is, we can find that, okay? Transpose, maybe not so much. Matrix of cofactors. Now, do we know what cofactors are?
Yes.
We've heard that before, we know how to find those, okay? Now, let's talk about what a transpose is. A transpose is what I like to call a right-hand pancake flip. Okay? And I'll show you what I mean by a right-hand pancake flip. Okay? It's different than a left-hand pancake flip. Okay? So, it is, believe me. Okay. So, we're going to take a look at these examples right here. We're going to look at example 3a, and it says, find the inverse of each matrix. And then it says, verify that you found the correct inverse to part A. So let's find the inverse to this right here, and I'm going to leave this visible right here. So if this is the matrix, okay, its inverse is going to be 1 over the determinant. So what do we need to find first? The determinant, okay? So let's find the determinant. Okay, now, first of all, can we find the determinant of this matrix?
Yes. Yes.
How come? Because it's a 2 by 2. What if it was a 3 by 3? It would be complicated, but we could find it. What if it were 2 by 3? You couldn't because it's not
Squared.
squared. Only squared matrices have determinants. So if you come across one where they say find the inverse and it's not square, can't do it because you can't find the determinant. Okay, so let's go ahead and find the determinant. 2 by 2s are pretty easy. This is going to be -6, and then this is going to be +8, correct? Okay, so the determinant is 2. You with me?
Yep.
Okay, so its inverse is 1 over the determinant, 1 over 2. Okay, now we're going to do the matrix of cofactors, and I'm going to put a T over this, and that T is going to remind me that I haven't done a transpose yet. I still need to transpose this. So let's do the matrix of cofactors. Now remember how cofactors work, okay? I need 4 numbers right here. So a cofactor is the minor with the correct sign in front of it. So what's the sign associated with this position? Positive. Cross out the row and the column. What's its minor? A 1. So we're going to put a 1 right here, okay? What's the sign associated with this position? Negative. Cross out the row and the column. What's its minor? -2. So I'm going to write minus minus 2, or the easiest thing to do would just be to write +2. Everybody good there? Sign associated with this position? Careful. Checkerboard of pluses and minuses, so it is negative. Okay?
And then
Cross out the row and column. What's the number? 4. Everybody good? Okay. Sign associated with this position? Positive. Cross out the row and the column. What's its minor? -6. Okay?
oh,
Right? Okay, does everybody agree that this right here is the matrix of cofactors? If this is the 2 by 2, this is the matrix of its cofactors. Okay, now, this is hard to show on the screen here, but let me show you up on this screen. If we're going to do a right-hand pancake flip, okay, if you're flipping pancakes, you normally don't slide the pancake flipper right in underneath it. If you're left-handed, you usually use your right hand and slide it in kind of on a diagonal. If you're right-handed, you kind of slide it in underneath as a right-hand diagonal. So I'm going to slide the pancake flipper underneath it like this, okay? And then I'm going to flip it over. Okay, now if I do that, look where the tip of my finger stays, and look where the palm of my hand stays, and look where my thumb goes. Okay? What numbers are going to stay in exactly the same place? The 1 and the 6, that upward right side diagonal. These numbers are going to stay in exactly the same place. But when I do a right hand flip, what's going to happen with the two of these? They're going to switch places. So this is 1/2, and now if I transpose this, the right hand pancake flip, the 1 stays in the same place, the -6 stays in the same place, -4 comes up here, and 2 comes down there. Everybody good?
Yep.
Okay, now, all of the hard work is done on this, okay? This right here is, whoops, let me make this look nice. This right here is the inverse. Okay, now, sometimes we'll leave it like that because what would happen if I were to distribute that scalar of 1/2 through there?
It would make weird stuff happen.
One of the numbers would turn into a fraction. So you can write it like this, or you can write it like this. Okay, this would be 1/2, this would be -2, this would be 1, and this would be -3. Okay, either one of those is fine. Everybody good there? Lily?
Could you distribute the 1/2 before the pancake flip and still get the same answer?
Sure. Yep. Usually it's easier to flip the numbers that are nice and then distribute through. In fact, a lot of times we'll leave it like this just because many times, depending on what these numbers are, I mean, imagine if the determinant was 1/7, or the determinant was 7. So this would be 1/7 out front. Then every one of these would be nasty fractions. Okay, yeah.
So on the test, would you do the first answer?
I'll take either one. Okay. If you have a 2x2 and you need to find the determinant, I'll take either one of these. If it happens that it's like this, everybody listen, please. If it's this nice, I'd probably go ahead and distribute through because then there's just one fraction. Okay? Everybody good? Sure? Okay. It says verify that we found the correct inverse. Now, remember what we've done here. We've found the matrix equivalent of dividing by whatever that original one was. So if the original number was 5, we've multiplied by 1/5, and we should end up with a 1. So if I take this and I multiply it by the original one, I'm going to change colors just so we can keep these straight. Okay? If I take the original one and I multiply it by its inverse, I should end up with the matrix equivalent of a 1. So I'm going to write down -6, 4, -2, 1, and I'm going to multiply it by its inverse, which is 1/2, -2, 1, -3. Everybody good there? Okay. Again, you don't have to do this all the time. We're just making sure that we all understand. This does actually work. It does actually produce the matrix equivalent of what we would get when we divide. Okay? So I end up with a 2x2. And if I take the first row and multiply it with the first column, so this would be -3 plus 4. -3 plus 4 is 1. Okay? First row, second column. First row, second column. So this is going to be 12 minus 12. 0. Okay. Second row, first column. Second row, first column. -1 plus 1. 0. So far, so good, right? Okay, this one is second row, second column. Second row, second column. So this is going to be a +4 minus 3, so I end up with 1. Okay, is everybody convinced that this is the inverse of that original matrix right there? Yeah.
Do you want us to prove this? Do this?
No. Okay, watch real quickly. Let me shrink this down. Okay, again, this is a branch of math called linear algebra. Okay, most books don't introduce this stuff. I find this an easier technique than what the book shows. Okay, it also builds on cofactors and the way we found determinants and stuff like that. Okay, normally all you'd have to do is write a matrix equation. You don't have to check and make sure that it actually represents the correct equation. And when we say find the inverse of the matrix, you find the inverse. What we did here is I was just basically convincing you, hey, this actually works. Okay, so is everybody convinced that we can write a system of equations as a matrix equations and we can actually find an inverse of a 2x2 matrix? Everybody good? Okay, let's keep going then. Okay, let's do this one right here. So I'm going to increase the size here just a little bit. Let's do part B. And all I want to do here is let's just find the inverse. So I'm going to change colors here. What do I have to do first? So I need to find the determinant. So the determinant is going to equal, let's see, negative 35 plus 30, right? So negative 5. So 1 over the determinant is 1 over negative 5. I'm going to put the t up there. So all I need to do now is just find the cofactors. Sign associated with this position. Positive. Cross out the row and column. What's the number I put there? Negative 5. Okay. Sign associated with this position. Negative. Cross out the row and column. Negative 5. Okay. Sign associated with this position. Negative. Cross out the row and the column. Negative 6. So minus 6. So I'm going to erase the negative and just write a positive 6. Sign associated with this position. Careful, positive. Cross out the row and the column. It's going to be a 7. Everybody good there? Okay, pretty simple. Okay, right hand pancake flip. Imagine, sliding our pancake flipper underneath this diagonal right here, and we flip it over. So this is going to be negative 1/5. And when I flip it over, these two stay in the same position, and these two switch places. So there's a negative 5 here and a 6 there. Everybody good? Okay, any questions? Okay, should we leave it like this with the scalar out front, with the 1 over the determinant out front, or should we distribute through? Probably leave it, because 2 of these are going to be ugly fractions, right? Okay, everybody good? Okay, if you did this, this would turn out to be a 1 and a 1. This would be negative, I'll do decimals, this would be negative 1.2, and this would be negative 1.4. Okay, or you could write them as negative 6/5 and negative 7/5. Everybody good there? Yeah.
Why do you have to use a transpose for that?
It's the way it works. Okay. We could go into a very, very long, week-long discussion about transposes and all that sort of stuff.
We should.
Okay.
No.
Right. Okay. Take a good look. Could we figure out, based on this method, a quick way to do it?
Probably.
Okay, now here's what I want you to look at. I want you to look at these numbers right here, and I want you to look at these numbers right here. There is no getting around finding the determinant. You have to have the 1 over the determinant out front. Okay, there's no getting around that. You still have to find the determinant. Okay, take a look at these numbers though. Do you see any patterns? Lily.
So you switch the 1 and then the 2 spots, and then you give a negative 2, and then you switch negatives? Or you apply a negative?
Okay, you apply a negative, I'll buy that. Okay, so I think here's what she's talking about. Notice that the 6 and the 1, all they did was switch places, right? And what happened to the 2 of these? They were multiplied by a negative. So they took on the opposite sign. Whatever sign they used to have, they now have the opposite sign. So let's check and see if this works on this one right here. So first of all, we're going to find the determinant. The determinant on this one would be negative 7 minus 6. So this is going to be 1 over negative 13, right? Now, what I'm hoping is we can get to this transposed thing without actually doing the minors or the transposing and stuff like that. So what we said is these two switch places. So what would happen with the negative 1 and the 7? They would literally just switch. That's going to be a 7 and that's going to be a negative 1. Okay, what happens to the 2 of these? They stay in the same place, but whatever sign they used to be, they now take on the opposite sign. So I'm going to put a negative 2 here and a negative 3 here. Everybody good? Okay. That right there is the inverse, and would we take the time to distribute a negative 1/13 through? Probably not. It's going to be easier. That entire thing together with the scalar out front is the inverse. If we did do this, we're going to end up with negative 7/13, 2/13, 3/13, And whoops, that's going to be positive, isn't it? Everybody good? Okay, you can write that down as the inverse, or you can write that down as the inverse. Either one of those is okay. The nice thing about this is, if you had to use it again, let's say we had to multiply another matrix by something, I'd rather multiply these nice numbers and then distribute a negative 1/13 through than try multiplying matrices with these ugly fractions. Everybody understand there? Okay, would you go ahead and do this one on your own? Would you go ahead and find the inverse of that? What's that?
Yeah. Because negative 5 and 6 still keep their signs whenever switched.
Does that not work?
We'll look at that in just a sec. What?
Does that not work?
What?
Because it's like, because it's negative 8 minus 8, which is 0, and then you can't do anything.
Okay. Why?
Because if the thing
Okay.
has the problem.
The determinant on this is 0. So out front would be 1 over 0. So can we find the inverse? Okay. Does not apply. There is no inverse to that particular matrix. No inverse to that particular matrix. Okay? Hey, we're recording. You get your name on this one too. Okay.
That's a nice shirt to wear today.
Skip class because everybody wanted to be his friend.
I'm not lazy. I'm really enjoy doing nothing. Okay. All right. So somebody had a question about, hey, does this work? Does this little pattern work on this one right here? Let's double check and see. Okay. We have to find the determinant either way. So that's going to be negative 5. Okay. Now we said these two switch places, right? So this is going to be 7. Whoops. This is going to be negative 5 and 7. And what did we say happens with these? They take on the opposite sign. So this is going to be a positive 6 and a negative 5. Isn't this what we got right here?
Yeah.
Okay. Does it work? Yeah. Yes, it does. Okay. Are there any questions?
Is this all we're doing for homework? Because that would be great.
That's pretty much it. But now we have to do a 3 by 3. Okay.
We stick with the 2 by 2.
Okay. All right. There are several methods for finding inverses for 3 by 3s. Okay, let me show you what the book shows you to do and why I think, especially if you had to do it by hand, it would be an unbelievable pain in the butt. Okay, what they say is take this matrix right here. Okay, don't write this down. You can read this in the book. Augment it with the identity matrix.
I think I'm.
Okay. And then do row operations until this one over here is the identity matrix. Yeah, you could do that. Think about how many arithmetic operations you have to do. Okay, and think about this. Listen carefully. Most inverses have fractions in them, which means nearly every one of these 9 numbers over here is going to turn into a fraction sooner or later, which is going to make the arithmetic on that unbelievably difficult. Okay? So I'm going to show you a way where we can avoid the fractions until the very end. Remember, we're keeping that 1 over the determinant out in front, and everything inside is just going to be a fairly nice number. Okay? So if you want to see how to do that, the book shows you how to do that. You're welcome to take a look at it. If you love row operations, you're welcome to do it that way, but keep in mind that on a test, you are not going to have the use of a calculator, okay? At least a graphing calculator. You can use a scientific one, okay? And it's going to take you much, much longer in order to find that, okay? All right, 3 by 3s do take a while, so let's go ahead and do this. Let's find the determinant. So let's go ahead and find the determinant. We can, let's see, row or column to expand on. I'm going to use the last column. So this is going to be sign associated, positive, numbers of 1. Minor is, cross out the row and the column.
0.
Sign associated with this position, negative. Number there's a 1. Cross out the row and the column. Sign associated with the position is positive, but it's 0. Does it matter what the minor is? It doesn't. I'm going to write it down anyway. Everybody good? Okay. So let's see. I have 0 minus 4, right? Here I have minus, and I'm going to have, let's see, a minus 3 and a minus 2, correct? So this is a negative 4 minus a minus 5 plus 5. What's nice about that?
I could get a 1.
What's cool about that?
It's like a really small even number, and it's 1.
Okay, it's not quite even, but I get your point. That means sitting out front is 1 over the determinant, so 1 over 1 is 1. So sitting out front is a 1. So I'm now going to write down, I'll go ahead and write down the 1 over 1, and now I need to find the matrix of cofactors. Okay? Now, this is a little bit on the tedious side. Please be careful with this. If you need to write down all of these separately, that's fine. We have to find 9 cofactors. Okay? We have to find all 9 of these numbers right here. Okay? And I'm going to go through and do this in an orderly fashion. I'm going to write a minus here, 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 and here, so I don't lose track of those. Okay? We're not going to do the pancake flip yet. Okay? It's much easier if you do it this way. Okay. So I'm going to find this minor right here. Cross out the row and column. 0 minus minus 3. What number do I put here?
3.
Positive 3. Okay? Next one. Cross out the row and column. 0 minus minus 2. So it is a negative 2 because remember that negative was sitting there to begin with. Okay, now is anything hard about this? It's just tedious, okay? Okay, next one. Cross out row and column. We already have the sign there. Cross out row and column. 0. Careful. Negative 4. Got it? Okay, now if you're using pencil, you can do the same thing I'm doing here. Okay? I'm going to cross out the row and the column for this one right here. I've already got the negative sitting right there, and then I look at this. 0 minus minus 3, so that's a plus 3. So I put it here. There's already a negative there, so this is negative 3. Everybody good? Okay. I'm just going to move it to the next column. I've already got the sign sitting out there. 0 minus minus 2. So this is a 2. Move this over again. Do you see how if you do this with your pencil, you can see what the minor is because you've crossed out the row and the column? Negative 3 minus 2. Negative 3 minus 2 would be negative 5. So this is going to be positive 5. So I'm going to erase this and put a positive 5 there. Everybody good? Okay? Okay. Now I'm down to this last one. Cross out the row and the column. Negative 1 minus minus 2. So that would be plus 2. So that's going to be a 1. Tedious and possibility for making lots of sign mistakes, but not hard math, is it? We haven't dealt with a single fraction. If you were doing this the way the book shows you, you would run into fraction after fraction after fraction. Okay, next one. 1 minus 0. So this is going to be a negative 1. Everybody good? Okay, and now I'm finally down to the last one. I haven't had to write down a whole bunch of stuff. Negative 2, 0, negative 2. Everybody good there? Okay, now, the only thing that we haven't done, what is that little T sitting up there reminding us of? We need to do a transposition, right-hand pancake flip. So we're going to slide our pancake flipper up underneath this diagonal and we're going to flip it over. So think about what happens here.
It's much more comfortable.
What happens to this diagonal right here? Stays exactly the same. 3, 2, negative 2. Okay? What happens to this diagonal up here? It flips down here, and this diagonal, or this triangle down here, flips up there. So here's what we end up with. The 2 and the negative 3 switch places. The negative 4 and the 1 switch places. And the 5 and the 1 switch places.
So they're basically like inverted.
Yeah, you could call it inverted. Okay, it's a transposition. This is what happens. This triangle up here kind of flops positions reflectively with that triangle down there. Okay? Okay. This is the shortcut for a 3x3. It doesn't get any easier than this if you're going to do these by hand. This right here is the answer because sitting out front would be the 1 over 1, which if you distribute a 1 through, it doesn't change that at all. Now, what would happen if this is A inverse and this is A? What would happen if I multiplied the two of those together? Should get the matrix equivalent of a 1. We'd get an identity matrix. 1's down the diagonal, 0 everywhere else. Everybody good with that? Okay, let me so any questions? Okay, let me slide this down and let's talk about this for just a second. Okay? Okay, it says you will need to be able to solve a 2x2 system by hand on the test using matrix equations. Okay? If there's a 3x3, I will give you the inverse of the matrix of coefficients. Okay? So that's going to save you a little bit of work, right? Now notice I didn't say I might give you a 3x3 and you have to find the inverse. Okay, you can kind of count on that, but then I'd hate for you to mess that up and then get the wrong answer to a system because you didn't get the inverse right. Okay? So I'll try and make it as easy as possible. So let's do this. Solve each system using a matrix equation. Let's do this one right here. By the way, does this look familiar? This is the same one, right? 1, 1, 1, negative 1. This is x, y, and this is 8, 4. There's our matrix equation. Yeah.
I have a quick question. So if you took the finishing matrix and multiplied it by the inverse matrix and multiplied it by the identity matrix, would you get the original one?
Oh, that's a good question. No, because if you multiply it by the identity, it turns into itself.
Okay.
It stays the same.
Is there a way to go backwards?
Yeah, what we just did. Do what we did in reverse.
Fantastic.
Start with this one and do 1 over the determinant times the transpose of the matrix of cofactors and you'll go back there. Okay? There's no short process to go from one to the other. Okay? Everybody good? Okay. So here's what I have. This is A, this is X, and this is C. What I need to do is I need to multiply by the inverse on both sides. So I need the inverse of this guy right here. So let's find A inverse. A inverse is, first of all, 1 over the determinant, negative 1, minus 1. Okay. Now, wait just a second. Did we do this one already? No, we didn't. No, we haven't found the inverse of it. So let's continue on. Let's find the inverse. So this is going to be 1 over 2. I'm going to put a t here. Or, wait a minute. On a 2x2, don't we know a quick way to get there? Okay, switch the two of these. What happens with this diagonal? They change signs. So this is a negative and that's a negative. Jared. Oh, it is. Thank you. Thank you very much. Okay. Everybody good there? Okay, so remember, the answer to this is going to be the inverse of the coefficient matrix times the answer matrix. So the inverse is negative 1/2. Negative 1, negative 1, negative 1, 1. And what is the answer matrix? 8, 4. Okay, let's check and see. Can we actually do this? That's a 2x2. That's a 2x1. Can I multiply? Yes, I can. Okay? I end up with a 2x1.